This lecture deals with measures of variability and is divided into two parts. Part 1 looks at several measures, including the index of qualitative variation, the range, and the interquartile range, and box plots. Part 2 looks at variance and standard deviation, and provides some considerations for choosing the most appropriate measure of variability for a given variable. So what are measures of variability? Well, they're summary measures used to describe how much variation or diversity there is in a distribution. In order to understand why that's important, consider the hypothetical grade distribution of two courses, one taught by Professor Brown and the other taught by Professor Yamamoto. Notice that the two have the same average value, about a C+. However, the two have a very different spread of data around that average. You can see that Professor Brown's grades are more tightly clustered around the mean, while Professor Yamamoto's are much more spread out, or less tightly clustered. In deciding which of these two courses you'd want to take, you'd want to know more than just the average or middle number. You'd also want to know how the data are spread out around that average. For example, if you wanted to get an A in the class, you'd certainly want to take Professor Yamamoto's class, because almost nobody in Professor Brown's course gets an A. However, if you were looking to avoid an F, it's much better to take Professor Brown's class, because nobody gets an F in his course. Let's start with the most basic measure of variability, something called the index of qualitative variation, or IQV. This is something that's used with nominal variables, and it's based on the ratio of the number of differences in a distribution relative to the maximum possible number of differences. IQV ranges from 0 at its minimum to 1 at its maximum, and it usually takes on values between 0 and 1. Often the value is multiplied by 100 and expressed as a percentage, and it tells us what percent of the maximum possible diversity is found in a distribution. Here's the formula for IQV. In order to calculate it, we need two quantities. The first is k, which is equal to the number of categories of the variable, and the second is a quantity called the sum of squared percentages, which literally involves taking each of the percentages, squaring them, and adding them together. Let's look at an example of how to calculate the IQV using data on the variable degree. The following table shows a distribution of highest degree, the variable, in this table. So, in order to calculate the index of qualitative variation, or IQV, we start by taking the percentages and squaring them. So, in a little bit more detail, let's look at the first category, less than high school. Notice that people who have a less than high school education make up 14.59% of the distribution. When we square 14.59, we get a value of 212.87. The next category, high school, makes up 49.44% of the distribution, and when we square that value, we get 2,444.31. Junior college makes up 7.65% of the distribution, and when we square that value, we get 58.52. So we do this for every category. We take each of the percentages and square them until we run out of categories. Next, we're going to add together all the squared percentages, and when we do that, we get a value of 3,145.14. So that's our sum of squared percentages. However, we also need the number of categories, and we can see here that this variable has 5 categories: less than high school, junior college, bachelor, and graduate degree. So k is equal to 5. Now that we have our sum of squared percentages and number of categories, we just need to plug those numbers into the formula. So the formula tells us to take k, or 5, multiply it by the quantity 100 squared, which turns out to be 10,000, and subtract that from the sum of squared percentages, which we calculated to be 3,145.14. That's the quantity we get in the numerator. In the denominator, we take 100 squared and multiply it by k, or 5, minus 1. When we do the arithmetic, we find that 10,000, which is 100 squared, minus our sum of squared percentages, 3,145.14, equals 6,854.86. And then in the denominator, we have k minus 1, or 4, times 100 squared, or 10,000, which is just 40,000. When we further do the arithmetic, we find that in the numerator, we get 34,274.29, and of course 40,000 in the denominator, which works out to a value of 0.85. Multiplying that by 100, we see that the value here is 85%, which means that this distribution is approaching 85% of maximum possible diversity, which is a relatively high amount of diversity, because it's closer to 100 than 0. The next measure of variability we're going to talk about is something called the range. And this is a measure that's used for interval ratio variables because it involves using some kind of arithmetic. The range is calculated as the difference between the maximum value and the minimum value. The range is a very simple, quick measure to calculate. However, because it uses only two measures, it could be picking up extreme or atypical values, and that may make it a misleading measure of variability. So, let's look at an example of how to calculate the range. Let's say that we wanted to calculate the range of an interval ratio variable, number of children. The following table shows the univariate distribution of number of children. Here we have both the categories of number of children, ranging from 0 to 8, the frequency, the percent, and the cumulative frequency. So how do we find the range? Well, we have to identify both the minimum and the maximum values. And we can see that the minimum value here is 0. And we find that it doesn't have a 0 frequency. In fact, 536 people indicate they have 0 children. So our minimum is 0. Next, we have to find the maximum value. And here we see that the maximum value is 8. And notice that there are at least 23 people in this category. That is, it's not 0. So we can confirm that our maximum, in fact, is 8. In order to calculate the range, we just have to take the difference between the maximum 8 and the minimum 0. And so 8 minus 0 gives us 8. How do we interpret that? Well, we would say that the people with the most children, the difference between them and the people with the least children is 8 children per household. We can also calculate something called the interquartile range, or IQR. This basically measures the range of the middle 50% of the distribution. It's a lot like the range, except it excludes the top and the bottom quarter of the distribution. That's really important because, like we said earlier, the range can be thrown off by extreme values. Therefore, this measure basically takes only the middle 50% of the data and ignores the values at the bottom quarter of the distribution and the top quarter of the distribution, effectively getting rid of those extreme values. So this is kind of a range that doesn't take into account potentially extreme cases. And again, this is something that's used for interval ratio variables because it involves some kind of numeric calculation. So here's the formula for the IQR. The IQR is basically the difference between the third quartile, or the 75th percentile, and the first quartile, Q1, or the 25th percentile. So, in order to calculate the interquartile range, we have to find the 25th and 75th percentiles. And we can do that using the cumulative percent columns. So, how do we find the 25th and 75th percentiles? Well, we have to find the categories that are the first to reach 25 and 75 in the cumulative percent column. But be alert. If the category lands exactly on 25 or 75, it's actually between that category and the next highest category, just like we found for the median in an earlier lecture. So, here's the distribution of number of children. Let's say that we wanted to calculate the interquartile range using this distribution. We have to locate two quantities. We have to locate the category that corresponds to the 25th percentile, or Q1, and the value that corresponds to the 75th percentile, or Q3. Let's begin with the 25th percentile. Looking at the cumulative percent column, which is the first category to include 25%? Oh, it's this one. It's the lowest category, 0, because you can see that the cumulative percent here is a little over 25. It's 27.19. Now, which is the first to include 75%? We see that it's this one, because this one's a little over 75, and it's the first to actually reach 75. So although it's 85.24, it's the first one to include 75. So our third quartile, or 73rd percentile, is 3. Now that we have the first quartile and the third quartile, we're just going to take the difference between those two to calculate the interquartile range. And so our third quartile is 3, our first quartile is 0, 3 minus 0 is 3. And so what does that tell us? Well, it tells us that 3 children separate the middle 50% of the distribution. Now, recall that our range was much higher than this. We found that 8 children separated the household with the most children from the household with the fewest children. But the middle 50% of the data are only separated by 3 children. That may suggest that somebody's having either a very high number of children or a very low number of children, and those values are extreme. When we don't consider those extreme values, we find that actually the majority of people, the middle 50% of the distribution, are only separated by 3 children. And so we may trust this value a bit more than the range because it's not as sensitive to outlying values. The next thing we'll talk about is something called a box plot, and this is a graphical device used to create a visual impression of some of the quantities that we've just been talking about, including the maximum, the minimum, the range, the first quartile, the third quartile, interquartile range, as well as the median. And this too is mainly used with interval ratio variables. Okay, so what does a box plot look like? Well, at the heart of a box plot is a solid box drawn between the first quartile and the third quartile, and the distance between the top and the bottom of the box is the interquartile range. Somewhere within the box is a solid line marking the median. And we have vertical lines extending from the ends of the boxes to the maximum and minimum respectively, which are called whiskers. Sometimes these things are called box and whiskers plots. So here's a stylistic box plot, just an illustration. Not every distribution is going to look like this, but this is good enough for illustrating a basic box plot. So, at the heart of the box plot, I said that there was a box. And this is a box that's extending from the first quartile to the third quartile. And of course, the distance between the top of the box and the bottom of the box is the interquartile range. Notice also that there's a dark band somewhere within the box, and that marks the location of the median. We then have vertical lines extending from the bottom and the top of the box to the maximum and minimum respectively. Again, these are called whiskers, and the distance between the minimum and the maximum, or the top and bottom of the whiskers respectively, is the range of the data. Box plots are very useful for making comparisons across distributions. In the following example, I'm going to show the differences in educational attainment for different racial groups using box plots. Notice that box plots can show both the overall shape of the distribution and how much variability there is within the distribution. So, let's take a look at these box plots. What can we tell from them? First of all, notice that we have 3 box plots, one for whites, one for blacks, and one for other. The first thing we can see is that the median is slightly different across these different racial groups. You can see that it's slightly higher for whites, and it's a little bit lower for blacks and other. In fact, blacks and other look like they have the same median. Most of them are around 12, although whites probably a little bit higher, maybe 13 or 14. So we can say the median education is a little bit higher for whites than the other racial categories. We can also say something about the actual size of the box. So notice that the largest box is for other, the smallest is for black, and then whites are intermediate between the two. And that basically tells us that the middle 50% of the data for other has the most variation in education, while for blacks, they have the least variation in education. And then whites are basically intermediate. But also notice that the box for whites is a little bit higher than that of the other two groups. And the floor is a little bit lower for that box, meaning that whites as a group sort of have more education if we consider the middle 50% of whites. What else can we tell? Well, we can see something about the maximum education, and that looks like it's 20 for both whites, blacks, and other. However, notice that the middle box plot for blacks has a dot indicating its maximum. So actually, some computer packages make non-traditional box plots in which they identify extreme or outlying values using things like circles. So it turns out that this maximum value for blacks is a little bit unlike the rest of the data, and it's being flagged as an extreme value, which is shown as a circle here. We can also say something about the minimum. We can see that the minimum for all 3 groups is the same, but again, we have dots indicating extreme or outlying values. So we can see that for whites, most of the people with low education are actually unlike the rest of the data for whites. They're found in the tails, and most of them are extreme values. For blacks, we have a few extreme values, but fewer than we have for whites. And then for other, they have the lowest overall low number if we don't consider extreme values, although the ones that have the lowest education for other are all extremes, are all unlike the rest of the data.